Day 135, Electrostatics homework, numbers 26 and 31. We did part A in class. You would have to draw a diagram to explain how the net electric field there comes out to be 0. But here's part B. Once again, this is a point particle problem. We have charges at the four corners of a square. Let me draw that. And then, once again, since we're talking about an electric field here, the equation we'll be using 4 times, but we'll take some shortcuts because some of the computations are the same. E equals KQ over R squared for the electric field at a given distance from a given point charge. So we have 4 positive 5 microcoulomb charges, and you can pick any one of the 4 sides here as your reference point. I'm going to take the bottom side, but the answer will be the same on all 4 sides. We have a location here where there's nothing there, so I'm indicating that with a blue dot. That's a location in space. And each of the 4 particles given will have an influence, will have an electric field that permeates that space. Let's start with the lower left. Once again, the electric field for a positive point charge goes away from that charge. And to summarize here, to simplify, what you would do is you would show, with reference to that lower left-hand corner, you would have an arrow, a vector arrow that shows you E, I'm going to call it E sub 1. That's the electric field generated by that lower left-hand corner particle. And I could calculate that because I know how far that is. That's 15 centimeters if the square is 30 centimeters on the side. However, I do not need to calculate that one because if you're looking ahead here, on the right-hand corner, lower right-hand corner, the field from that positive 5 microcoulomb charge is just opposite that. It's pointing towards the left, away from that charge. So its field, let's call that one E sub 2, would have the same magnitude but opposite direction. Those would cancel. Once again, vectors can cancel if they're opposite like that and equal in magnitude. The problem comes in now with the next two, or the bigger challenge, because these vectors will be at angles that need to be added with components. For example, if I look at the upper right-hand corner right now and imagine a straight line, and I'll make a dash line just to kind of show you this, from that upper right-hand corner down toward this location, that upper right-hand corner 5 microcoulomb charge creates or has a field that points this way along that line. I'm going to call that E sub 3 relative to that upper right-hand corner particle, linearly, radially outward from that. And likewise, from the upper left-hand corner, same thing holds true. If I drew a line from that direction, there's going to be a field that's along that radial direction. We'll call it E sub 4. But E sub 3 and E sub 4 are the same size. E sub 1 and E sub 2 are already canceled, in our mind at least. But there are 4 fields here we have to combine, and the 2 cancel, so all we have to do is combine the E3 and E4. However, they're the same magnitude, so if I calculate them, E sub 3 is going to be 9 times 10 to the 9th times the 5 microcoulomb charge divided by the distance squared. But how far is that blue dot from the upper right-hand corner? Well, this requires some geometry. Let me draw this. I drew the square a little smaller, the 4 corners of the square with the blue dot in the middle of the bottom side of that square. But if I draw a diagonal from this upper left-hand corner to that location, that triangle just formed, I know that this distance right here is 15 centimeters, and this was given at 30. 15 is half of 30 because it divides that bottom half. So I need to find, let's call this R here, simply by the Pythagorean Theorem. R squared equals 15 squared plus 30 squared. So R comes out to be 33.5 centimeters. You can say 34 centimeters if you wish. 34 centimeters. That's how far it is from the upper right-hand corner. So that's what I'm going to plug in for E3, the distance for the field from that charge. Back up here on the upper right, it's 34 centimeters, actually 0.34 meters. I need meters. Squared So if I calculate E sub 3, which will also be equal to E sub 4, I'll just write that down. They're both the same size. Comes out to be 4.0 times 10 to the 5th newtons per coulomb. 4.0 times 10 to the 5th newtons per coulomb. That's what E3 and E4 are. Now I need to add E3 and E4, and they're not lined up perfectly, so now we have to find components. But you'll see once again that there'll be some shortcuts. Let me run through that. I'm looking back down here on the lower left now. Let me just draw E3 by itself. E3, I'll draw a little longer just so I have more space. E3, we just found out, is 4 times 10 to the 5th newtons per coulomb. 4.0 times 10 to the 5th newtons per coulomb. Well, it has a y component and an x component. Same thing for E sub 4. I don't really need to draw it, but I will. It's the same magnitude, 4.0 times 10 to the 5th newtons per coulomb. And it has a y component and an x component. But the x components of both these two vectors will cancel out. What will be important here is the y components. They're both in the same direction. All we need to do is figure those out, or figure one of those out and double it for the answer. So I need to know this angle right here, which is the same as this angle over here. And once again, because of the geometry of this situation, this angle up here and this upper right-hand square is also the same angle. That theta, that blue theta that I have right in that diagram in the middle of the page, I can easily calculate using tangent. Tangent of theta equals 15 over 30. Turns out that theta is 27 degrees, rounded off to 2 sig figs. So it's the same theta that's in the vector diagram, component diagram for E sub 3 and E sub 4. So now I know theta. And what I'm really looking for, going back to the lower left here of the diagram, I'm looking for the y component. I'll just label it EY, the y component for either one of those. It's the same value for both of those. I can put it on either diagram. And to calculate that, all I need to do is use cosine, and that triangle right there, and I'll go all the way over to the right, but I'm looking at these diagrams on the lower left. If I take the cosine of that angle, which is 27 degrees, I'll do the math over here on the right. So cosine of 27 degrees will equal the adjacent leg, the E sub y that I'm looking for, divided by the 4 times 10 to the 5th. 4 times 10 to the 5th. All right, I go to my calculator. E sub y for both of those blue vectors on the lower left is 3.6 times 10 to the 5th. And that's newtons per coulomb. But that's each one of those individually. The net field now is just the sum of those two. In other words, just double that. So my final answer is E net equals 3.6 times 2, which is 7.2 times 10 to the 5th newtons per coulomb. And that would be perpendicular and outward at each side. Perpendicular and outward. That's the net field at the midpoint of each of the 4 sides of this square. Put a box around that. 7.2 times 10 to the 5th newtons per coulomb net electric field at the midpoint of each of the 4 sides. Alright, I just decided I'm going to do problem number 31 in a separate video. So if you want to watch these videos individually, it'll be a little easier.